So today we're just going to do a couple questions relating to fundamental principles again. So first we have a question on uncertainties. So a solid cylinder has a diameter of 2 plus or minus 0.02 centimeters and length 4 plus minus 0.02 centimeters and mass this. So what is the density and uncertainty of the solid cylinder? So what I want to do first is convert these units into SI units. And also I noticed that we have a diameter, and the formula for the volume of the cylinder, which we will need, is a formula dependent on radius, not diameter. So our radius will be 1 plus or minus 0.02 centimeters, because sorry, this should be 1, because I'm just getting half of the diameter. And then in meters, this is just 1 plus or minus 0.01 times 10 to the minus 2 meters, because there is 100 centimeters in 1 meter. So that's why we do the 10 to the 2 multiplication. And then our length, this is the same thing. We don't have to do anything to it because we use the length in the formula. So this is times 10 to the minus 2 meters. And then our mass is equal to 106.81 plus or minus 0.01 times 10 to the minus 3 kilograms, because there's 1,000 grams in a kilogram. Now I need to, I want to find the density of the cylinder. So density formula is, so density has the symbol rho. So this is a Greek letter. It just looks like a P, which is mass over volume. So the density of the cylinder will be the mass of the cylinder over the volume of the cylinder. Now, the volume of the cylinder is going to be the area of this face times the length. So the area of the circle of the face is pi r squared, and then the length is L. So this is our formula for density, and then we can find it just by plugging in each of these values without the uncertainties. So we will get 6.81 times 10 to the minus 3 over pi times 1 times 10 to the minus 2 squared times our length, which is 4 times 10 to the minus 2. So this is going to be equal to 106.81 times 10 to the minus 3 over, well, that becomes 1 squared, and then that 10 to the minus 2 squared is just 10 to the 0, so that's just 1. No, it's not. It would be 10 to the minus 4. So 10 to the minus 4, and then 10 to the minus 4 minus 2, you get 10 to the minus 6. So it would be 4 times 10 to the minus 6 pi. Now you don't have to do this part, you can just plug this into your calculator, but I'm just making it a little bit easier for myself. So 106.81 over 4 pi multiplied by 10 to the minus 3 minus 6. So this is 10 to the minus 3 minus minus 6, which is 106.81 over 4 pi minus 3 plus 6 is 10 to the 3. So then we can put this in a calculator, 106.81 over 4 pi, and we get 8.499, so 8.5. But because we have 10 to the 3, this is just 8,500, but this is in 4 significant figures, so maybe it is more appropriate to write 8.50 times 10 to the 3 kilograms per meters cubed, because kilograms and meters cubed there. Now we need to find the uncertainty in our density. So the uncertainty in our density, or I should say the fractional uncertainty in our density, is going to be equal to the power of the variable. So this is 1 times the fractional uncertainty of the variables present in our equation. So because our radius has a power of 2, we will have a 2 at the front, and then it would be our fractional uncertainty in our radius. And then because there's just nothing on the L, it will be power of 1 delta L over L. And now we can plug our values in. This is just delta M is 0.01 times 10 to the minus 3 over M, which is 106.81 times 10 to the minus 3. Now what we notice is that for all 3 of these terms, we will have common factors in both the numerator and the denominator, and these just cancel. So for the radius, we can write this as 2 times 0.01 over 1. We don't have to write this part here because it appears in the numerator and the denominator and it's redundant. And then for delta L over L, we can just do 0.02 over 4. So this is going to be equal to 0.01 over 106.81, 0.01 over 106.81 plus, so 2 of this would just be 0.02 over 1, so plus 0.02, and then this is just 0.01 over 2, because I'm just simplifying this fraction, so 0.01 over 2, which is 0.005 plus 0.005, and we get this value here, so 0.025. This is our fractional uncertainty for our density. Now, what we need to do is to obtain just our uncertainty in density alone, we will have to multiply both sides by this density here. So then we get our delta density to be equal to 0.025 density, which is equal to 0.025 of this value that we calculated here. So 8.5 times 10 to the 3, which is equal to answer times 8.5 10 to the 3, 8.5 times 10 to the 3, we get 213.29. So three significant figures would be 213, 213. Again, this would be the same units. So then our final answer will be 8.5, 8.50 times 10 to the 3. But we want this to be 10 to the 2 maybe. So we'll rewrite this like this. So 885.0 times plus or minus 2.13 times 10 to the 3. Sorry, not 10 to the 3. Times 10 to 2 kilograms per meters cubed. And the reason why I wrote this as 85.0 is because now I can write both of these with the power, the factor of 10 to the 2. So it makes my answer look a bit cleaner. So that's our answer. Intersection. Okay, so we'll do this question now. At the instant traffic light turns green, a car that has been waiting at the intersection starts ahead with a constant acceleration of this. At that moment, a truck traveling with a constant velocity of this overtakes and passes the car. So we can sort of think of this scenario as, so this is our car here. And then, so this car is going to accelerate at 2 meters per second squared. But at that moment, a truck which is already driving, so a truck is isn't starting from stationary, the truck will come and pass it. So this truck is traveling at 15 meters per second. Now, what is the time necessary for the car to reach the truck? So we're going to use a kinematic equation. The equation that we use, I think, I've just got some formulas here that I'm looking at. So it will probably have to be a formula with a t given. So we can try and use Vf is equal to Vi plus At, but we don't want to do that because we don't have a displacement. So what we would actually want to use is this equation here. V, so xf equals xi plus vit plus 1/2 at squared. So this equation should be all we need to solve this problem, just part A. So we need to find the time so that each of these vehicles have the same displacement. So what we can do is let's set up two equations, right? So we'll have xf of our truck equals xi truck plus vi truck plus 1/2 a truck t squared. And then we'll have our xf of our car equals xi car plus vi car plus 1/2 a car t squared. The reason why I'm doing this is just so we can specify each quantity that pertains to each vehicle. And what we want to find is the value of t such that x f of the truck is equal to x f of the c. So the final displacement of the truck is equal to the final displacement of the car. Now, to do that, we just apply this. What we find is xi of your truck plus vi truck plus 1/2 a truck t squared is equal to xi car plus vi car plus 1/2 a car t squared. And now we can try and do some simplifications. So we know that the initial displacement of the car is 0. So we know that this is 0. And we know that the initial velocity of the car is 0. Now for the truck, we know that the acceleration is 0. It's not accelerating. So I should maybe do this in another color. So this is 0, this is 0, and then the acceleration of our truck is 0. However, we know the velocity, and we're going to say that its initial displacement is 0 as well, because we're going to assume that we're measuring both of these from rest. Or not from rest, but we're going to set 0 as being where the traffic light is. So now we get vi of your truck, that whole thing is 0, equals 1/2 a c of your truck times t squared. So now we solve for t here. So that means that we times both sides by 2. So if you do 2 times this, and then 2 times this cancels with that. And then what you're left with is 2vi your truck equals your acceleration of your car times t squared. Now, to get t squared on its own, divide both sides by your acceleration of your car, and we find that this cancels. So then we get 2vi of your truck over your acceleration of your car equals t squared. And then to get rid of the power of 2, you get the square root on both sides, and the square root cancels with that power of 2, which means that your t is equal to the square root of 2vi of your truck over your acceleration of your car. So then we plug in our values here, right? So our velocity of our truck is this, and our acceleration of our car is this. So our answer is just t equals the square root of 2 times 15, 30, over the acceleration, which is 2, which is just the square root of 15. So let's just do this. Square root of 15 is 3.87. 3.87 seconds. Okay, now for B, the distance that the car will pass the truck. The distance will just be your, so this is for the car. So we'll just need to use another equation. We'll just need to do xf equals xi plus VIT plus 1/2 AT squared. But for the car, this is 0, this is 0. So then the displacement here will just be 1/2 of 2 times 3.87 squared, which is just 3.87 squared because this is just 1. So 3.87 squared, you get 14.97. 14, 9, 8, 14, 15. So you get 15 meters. Or in 3 sig fig, 15.0 meters. And then see the speed of the car when it passes the truck. So we would need to find our final velocity. So we need to use a different equation. Namely, we would need to use this equation here. VF is equal to VI plus AT. Now here our initial velocity is 0, and our acceleration is 2, and our time is 3.87. So our final velocity, I should probably specify of the car, so that's just a little c. This will be 6, I can't remember, this is 6, so 774, I think. Sure, I might be wrong. So 3.87 times 2. Yeah, 774. Okay. So don't need to do that.